Hello, everyone. My name is Haitao Yuan. Today, I will share my paper, whose name is Road Travel Time Estimation on a Road Network, Revisited, Heterogeneity, Proximity, Periodicity, and Dynamicity. The first question is, why we need to estimate the travel time? Actually, it's more and more popular for us to enjoy online ride-hailing services. One of the most important operations is to estimate the travel time from one point to another. Hence, you can arrange your time well, especially when you have a busy schedule. So we focus on the travel time estimation problem. More specifically, giving a request that consists of a route and a departure time, how to estimate its travel time. This problem has been studied for quite a while. Existing studies can be broadly divided into two categories, the long learning method and the learning-based method. Firstly, the respective long learning solution is called statistics-based method. Given a query, they estimate the travel time by averaging the travel time of a historical recorded trajectories. Secondly, there are two kinds of deep learning methods. The first uses the recurrent neural network. In particular, they regard the route as a sequence of links and apply some sequence encoding models to achieve the goal, such as the LSTM. The second uses the graph neural network. They leverage the gravitation model to independently capture each link's contextual features for a given route. However, existing methods cannot fully exploit spatial-temporal features from the following aspects: heterogeneity, proximity, periodicity, and dynamicity. As for the spatial heterogeneity, it behaves in at least two aspects. The first is that the turning ways between different links in a neural network are heterogeneous. So they makes the travel time of same link various. The second is that different links contain heterogeneous attributes, which means that different links should correspond to different travel time as the same, even at the same time slot. As for the spatial proximity and temporal, as for the spatial proximity, we should consider the neighboring links are under topological constraints of a neural network. So how to capture this constraint when we encoding our spatial features? As for the temporal periodicity means that the travel time of each link exhibits periodic acceleration characteristic for a week. So we should capture this periodical acceleration characteristic when we encoding our temporal features. The last is called the dynamic traffic conditions. For example, at different times the traffic should be different. So we should consider the dynamic conditions when we want to estimate the travel time for a given route. So though our goal is to design a generic learning framework to incorporate all the above critical aspects. To achieve this goal, we should face the following three challenges. The first is that the spatial heterogeneity, and proximity playing opposite roles in the estimation task, which makes it difficult to learn different links representations. For example, the spatial heterogeneity means that the travel time should be different, while the proximity means that the travel time should be the same. The second challenge is that there are both collections and the difference between the influence of static and dynamic features on the travel time. So how can we design a method to distinguish them? The last is that remains a key challenge to design effective models to capture complex spatial-temporal correlations. So, to begin with, we have proposed some key features to solve this problem. These features can be included into three kinds. The first is called spatial-temporal features, which mainly includes the historical traffic conditions to capture the dynamicity. Well, in particular, these conditions include the minimum, the maximum, the medium, and the mean travel speed. The second is the spatial only features, which includes the global root network and the local root graph. As for the global root network in the figure shows, we convert this root network into the link collection graph, which is a heterogeneous graph with 4 kinds of edges, to denote the different turning ways. And we also exclude the local graph from the whole graph. Well, this local graph is the subgraph of the link collection graph, and we call it the root neighboring graph. It includes the root link, the spatial root past links, and the adjacent links. The last kind of feature is called temporal only features, which mainly includes the temporal background information, such as the rush hour, weekdays, and other time-related informations. Next, we proposed a pipeline to estimate the travel time. This pipeline includes 3 steps. The first step is to prepare the data, which means extracting key features. And we further divide this feature into 2 kinds. The first is called the sample-wise general features, which means the different samples should share these features. And we use these features to generate the general representations. And then the other feature called sample-wise spatial features, which means that these features should be different for different samples, including the C means the traffic conditions, FRGR means the root neighboring graphs related features, X means the temporal background information, TS is the departure time. And next, based on these extracted features, we design 2 streams to generate the travel time. The first stream is a static generator, where we use the general features to generate the global static speed histograms, and then we fetch the local speed histograms for the given route. Next, we combine the local histogram and the spatial features to generate dynamic histograms in the second stream. And last, we design the travel time generator, which could generate link travel time based on the estimated speed values or histograms. We also proposed a model called STHR to achieve the pipeline. As the figure shows, we first prepare the features, and then we design 2 paths to achieve the travel time generation. The first part is called the temporal encoder, which aims to encode traffic conditions and temporal information. And this path includes 3 key modules, namely the traffic condition fusing module, the temporal self-attention module, the time slot attention fusing module. As for the spatial decoder, which aims to generate local dynamic histograms, and this part includes 4 modules, namely the global static histogram generator module, the local static histogram feature module, the spatial temporal attention module, and the dynamic speed generator module. As we can generate the dynamic speed histograms, we can estimate the route travel time in the last steps in the last step, where we first compute the link travel time, and then using the loss computation paths to compute the loss, and using the loss to learn the whole model's parameters. Next, I'll introduce some details about the two parts. As for the temporal encoder, which includes the three important modules. The first module, traffic condition fusing, is to capture spatial correlation among traffics, dynamic traffics. In particular, we use the graph attention neural network to encode each link's past traffic conditions in the local graph, because we want to capture the local spatial correlations. And last, we using the temporal self-attention module to capture temporal periodicity among traffics, to further capture the temporal periodicity among traffics. And last, we to fuse the temporal information and traffic, we design the time slot attention fusing. In particular, we compute the similarity between the current and past temporal informations as the weight, and then using the weighted summation to fuse the temporal information into the traffic encoding results and get the unified temporal representation. As for the spatial decoder, which also includes three modules. The first module is called the global static histogram generator, which can generate the global joint embedding of link and time slots, which we first using the graph attention network to capture the spatial correlation among links, and then we use the time slot embeddings, which includes the day in week embedding and the time in day embedding. The last is the local static histogram feature. We use this module to look up local joint spatial temporal embeddings for the given route. And last, we fuse the representation with temporal encoder results and get the spatial temporal final representation. Okay, we have done some experiments to evaluate the performance of our model. We use 3 taxi order datasets, which are collected from cities of Chengdu, Xi'an, and Nanjing, respectively. We also select some baselines to compare. The first 2 baselines is called the long learning method, which use some historical data to estimate the travel time. And the last 3 methods is called the deep learning method. And the last is an ensemble method. And first, we compare the effectiveness. As shown in the table, we compare our model SGHR with 6 baseline methods. Also, to evaluate the different paths effectiveness, we get 4 variations of our model by replace different paths of the model with fully collected neural networks, which are respectively denoted as NR, NL, NT, and NS. We find that our model is the best model. In addition, the variation NS has a worsened performance than other variations, which means that the spatial temporal attention is the most critical part of our model. Later, we further compare different methods' efficiency. As shown in the table, we have the following findings. First, the long learning methods require more memory than others because they need to load data information whose size is proportional to the size of historical trajectories. And the deep learning method DTravel has the same model size for data, but others are different because other methods consider size of neural network, which varies from one city to another. The last observation is that due to the computation complexity of graph neural network, our method and the state-of-the-art method consume more training and estimation than others. And in addition, we also compare the scalability and get 3 findings. The first is that all methods perform better if more trained data is used. The reason is that more data indicates more situations, making the model learn better. The second is that deep learning methods are more stable and effective than the long learning methods. The last is that our method is more stable and more effective than others. Okay, that's all. Thank you for listening.